Next problem is number 9. The object initially on the ground is accelerated vertically by a rope. It reaches 3 meters in 1.5 seconds. What's the tension in the rope? So we're given that its initial velocity is 0. Its displacement upwards is 3 meters. And the time is 1.5 seconds. That's enough information for us to calculate the acceleration and then use net forces to find the tension in the rope. So, the equation we can use is delta y or delta x equals vi t plus 1/2 at squared. So 3 meters up, starting from rest, acceleration 1.5 seconds squared. So off the acceleration you get 2.67. And then the net force equals ma equation. The only force, well, not the only force, there are two forces here. We've got tension going up, we've got force of gravity going down. So when we subtract them, Ft minus force of gravity is 2 times 9.8, which is 19.6, equals 2 times the acceleration we found. Solve for Ft, and you get 24.93. Number 10 says a 5 kilogram block accelerates down the ramp at 4.2 meters per second squared. What's the coefficient of friction? So our force diagram, you got mg going down, Fn. There's friction here, so as it slides down, you got force of friction there. I'm going to do this whole problem without using the massive 5 because you don't need it. But if you needed it, if you felt like you needed it, you can use it. So this side, there's theta, this is mg sine theta, mg cosine theta. The only two forces that are the same are mg sine theta, or mg cosine theta, as well as the normal force. Since this thing is accelerating downhill, friction and mg sine theta are not equal. In fact, I should probably drive my force of friction as just a small force here, because our net force down is causing the acceleration down the ramp. So I'm going to call down the ramp positive. So when I do F net equals ma, I've got mg sine theta pointing downhill. I've got force of friction pointed uphill, and force of friction is mu times the normal force, or mg cosine theta, and that equals ma. So again, the 5 kilograms is not necessary. We just left it in case somebody wanted to try and use it, which is fine. The only thing we don't have here is mu. You have everything else you need. Solve for mu using algebra and you get 0.16. Number 11. Which graph shows the relationship between acceleration and net force? So net force equals ma. This is Newton's second law. We're looking for the relationship between acceleration and net force. So assuming your mass stays the same, if you have a bigger net force, you have a bigger acceleration, and vice versa. If you had like a smaller acceleration, it must be because the net force was less. So the direct relationship here is D. Number 12, we had a problem like this in our homework packet. 75 Newton force pushes the block against the wall. It gives you mu. How heavy could that block be but still not fall down the wall? So force diagram for the block, you got F pushing to the right. You must have a normal force pushing outward. That's the same because it's not going through the wall. Friction is pointing up, and force of gravity is pointing down. Those have to be in equilibrium. It gives us mu, and we want to know about a mass. So we're mainly going to focus on the force of friction and the force of gravity. We know that they are the same. I don't need to do F equals ma here because there's no acceleration going on. So mu times the normal force equals mg. Our normal force is F. We already labeled it as being the same. So 0.65 times 75 equals m times 9.8. Solve for m, and it's 5 kilograms. 13. A 45 kilogram woman is standing in an elevator that's accelerating downward at 2 meters per second squared. What normal force does the floor exert on the woman's feet? Okay, so 45 kilograms times 9.8 going down is 441 newtons. And if the elevator is accelerating down, that means the force down is bigger than the force up. So normal force, which is what we're looking at. If I do net force equals ma, I've got normal force going up minus 441 going down. Mass is 45, and our acceleration downward would be -2. So -90 plus 441 gives us a normal force of 351 newtons well enough. 351 is not a choice over here because this is going by significant figures. There's 2 significant figures there, 2 figures there, so our answer's in 2. So we'll throw back to your chemistry days. Number 14. An object moving to the right is slowing down. The net force must be. So if our object is moving to the right, slowing down, let's just say it's like sliding on the ground, it would have a force of gravity, a normal force, and then it would have a force of friction going to the left. So since it's slowing down as it goes to the right, the net force has to be to the left. 15. The acceleration of the system. This is an Atwood problem. It's just the car is not hanging straight down. It's just on an inclined plane, which is fine. So I'm going to do 2 force diagrams, one for the block, one for the cart. For the block, we've got a normal force up, force of gravity down, which are the same. You got friction to the left. You got tension to the right. For the cart, you got mg going down, force of gravity going down, you got your normal force going up. You got your tension force uphill because it's from the string. And there's no friction on the incline, so we don't have to worry about that, but I am going to take the force of gravity and break it into its 2 components. M2g sine theta, M2g cosine theta. That has to be the same as the normal force. Our tension forces in the diagrams are the same. I'll give them 3 tick marks. And again, we do these Atwood problems looking at the system as a whole, so the tension forces we don't have to worry about. When I'm looking at the net force equation now, I'm looking at forces that are in the plane that the objects can move. So I don't really concern myself with the normal force and gravity force too much on the block. Normal force is going to come into play with friction, but normal force itself is not going to be part of the net force equation. So instead, in the net force equation, we've got, I'm going to call downhill positive. I've got m2g sine theta, that's going downhill. And I've got force of kinetic friction on the block going uphill, so I would subtract it. That all equals m1 plus m2 times the acceleration. Those are my 2 forces that contribute to the net force of these objects moving along the plane that they're moving. So m2g is 12g sine 42 minus, this will be mu, gives us this 0.23 times 15 times g. No sign or anything needed there because the block's on a flat surface. Equals 12 plus 15 is 27 times a. So the only thing you don't have is a. Do your algebra, solve for a. It's 1.66 meters per second squared, and this is all moving in the clockwise direction. Couldn't possibly be going in the counterclockwise direction. A block of dry ice is pulled along a tabletop with a constant acceleration, and we're going to assume there's no friction, which is nice. So what forces act on the block as it's pulled across the table? So for part A, you've got this. You can either call it an applied force or a force of tension. There's a hand exerting the force on the string, so whichever way you want to call it, force of tension, force applied. We'll just call it force of tension. force, gravity, and no friction. And G slash applied, whichever way you want to call it. At point B, the rope breaks. What forces would be acting? Well, now it's just Fn and Fg. As it slides, it would be sliding at a constant velocity. As the block slides off the table, now it's in the air. Prior to landing, you would just have the force of gravity, assuming there's no air resistance, which we pretty much negate unless otherwise stated. 17. A mass is pulled across the floor by an applied force. Assuming there is no friction, if the mass of the block doubles, how must the applied force be changed to maintain a constant acceleration? So again, F net equals A. We're saying that the mass doubles. Now we have twice as big of an m. If we want to keep the same exact acceleration, that means you must have twice as much net force, so that the ratio there stays the same. So net doubles. F net here is the applied force. If the applied force is changed to be applied at an angle below horizontal, what will happen to the acceleration? So if instead of pulling to the right, now we're pulling down and to the right, the x component is now smaller than the original force. Like if this was 10, this might now only be 6 newtons to the right. So that's going to have a smaller net force, which means you have a smaller acceleration. Uh, 18, the block hits a rough patch, causing friction between the block and the surface. In order to maintain the same acceleration as before, what must happen to the applied force? Well, now we've got some friction to oppose. So if we want the same net force or same acceleration, our applied force has to increase in order to have the force of friction subtracted and still give us the same net force as before. So Fa has to increase. B, if the block moves at a constant speed, what's the force of friction? It would be equal to the applied force. C, if the applied force is changed to be applied at an angle above horizontal, what happens to the normal force? If we're pulling up, the normal force doesn't have to be as big because now there's an upward component, so the normal force can be a little bit less. The ground doesn't have to support the full weight of the object, so normal force decreases. Force of friction then would also decrease because the normal force decreases, and that's part of the equation for frictional force. The net force, again, if you're applying it to the right compared to up and to the right, your net force to the right decreases. Although it's not actually proportional to force of friction, it does actually decrease. Alright, I'm using the diagram of the Atwood machine at the right. How is it possible for the masses to move at a constant velocity? Well, that's only going to be possible if our masses are the same, because you'd have the same force up and down for both blocks. And they would also have to be moving you'd have to cause them to move, and they would continue moving at a constant velocity. This is like a Newton's first law thing. Object in motion stays in motion. For these things to move at a constant velocity, somebody would have to make them move and then let go, and they would continue moving at a constant speed. B, if M1 is greater than M2, what direction is M1 going to go? If M1's more massive, it's going down. M2's going up. C, is it possible for the masses to have different magnitudes of acceleration? Magnitude here, by the way, if you can't remember that from before, magnitude just means a number answer. It doesn't have a direction at all. So can they have different accelerations, whether it's up or down? No. Whatever the acceleration is of one, it's the same as the magnitude of the acceleration of the other. D, solve for the acceleration of M2 if M2 is greater than M1. I am actually at the end of the length of this video, so I'll finish D and do number 20 in the next one.